I'm just waiting for the stream to show up on my YouTube thing here. Okay. I'm just waiting for the stream to show up on my YouTube thing here. Okay. I'll wait 1 more minute and then we get going.
Mm-hmm.
All right. Good evening, everybody, or good morning, wherever you are in the world. Very welcome to this first live stream, live stream on advanced Haskell topics. My name is Ed de Vries. I'm a senior consultant here at Well-Typed, but my role here today will be merely a moderator because it's my great pleasure to introduce Finley McElwain, who is a fairly recent addition to the Well-Typed team and who has very kindly volunteered to give this first seminar on debugging techniques for memory problems with Haskell. Before we get going, a few intro remarks. We would like this to be interactive. So if you have any questions or any remarks that you would like Finley to address in the lecture, do put them in the chat. There's a bit of a delay between the live stream and us talking, so it can't be quite back and forth. But if there's any questions or comments, do put them in the chat. I will keep an eye on this, and if I feel like they will be useful to address for everybody, then at a suitable moment, I will interrupt Finley. I will and then put the question on screen, and we can talk about it. So yeah, do ask questions. Then, if you or your company would like help with memory profiling issues with Haskell, or indeed any other Haskell-related task, we at Well-Typed are, of course, a Haskell consultancy company, so come and talk to us. Conversely, if you feel you already know all this stuff and you would like to come work for us, or you know anybody who does, then we are hiring at the moment, so also get in touch then. Finally, this is our first time doing a live stream like this, so it's a bit of an experiment for us. So if you have any feedback on the format or the approach, or indeed if you have any suggestions perhaps for future topics, then let us know either in the comments below, or email us, or tweet at us, or however you wish to contact us. But we would love to hear your feedback. And with that, I think I will give the floor to Finley and take it away.
All right, thank you. So yeah, this is a workshop on profiling memory usage using eventlog2html and ghc-debug. And in addition to those tools, we're also going to be talking about a tool written by EDSCO named thunks, but that'll be just a slight detour. Preliminaries for this workshop is kind of like the prerequisites. You kind of need to understand lazy evaluation, normal forms, Haskell's semantics as a lazy programming language. All of those topics are very important to understand sort of how memory does get allocated by Haskell programs and from the get-go. So, but I hope that the content we cover should be helpful for Haskell beginners and experts alike. So first, we're going to start by looking at ghc-debug. And ghc-debug is not your typical, it's not a traditional debugger in the sense that that you're used to working with, especially from imperative languages. In ghc-debug, it's a sort of different style of debugging where we have two concepts, one being a debuggee and one being a debugger. And the debuggee is the application that you've instrumented that you want to look at under the microscope of ghc-debug. And a debugger is what talks to the debuggee and get statistics about the heap and the memory usage of the program, and then can report those statistics. So communication between the debuggee, which is your application you're debugging, and the debugger happens over a socket that gets created by the debuggee. And over that socket, the debugger makes requests, and the debuggee will respond to those requests with information about the heap. And those requests are specific, like those requests are handled by another thread in the debuggee that talks to the runtime system and all of that. So one very important feature or aspect of this is that it's very easy to turn any Haskell application into a debuggee that can be analyzed by ghc-debug debuggers. And we'll see how easy it is later. So with that in mind, knowing that we have a debuggee and a debugger, debuggee being the application that you are debugging, and then the debugger being your what you're looking at that application with, we can introduce ghc-debug as just a set of libraries. One of the libraries is ghc-debug stub, which contains all the library functions that you need, or the library functions that you need to turn your Haskell application into a debuggee that can be analyzed by a debugger. ghc-debug client has functions so that you can write your own debugger scripts. So you can write custom sort of domain-specific debugger scripts using ghc-debug, and then run those scripts on any debuggee. And then ghc-debug brick is a terminal user interface application that was developed by us at Well-Typed. That's sort of just a generic debugger that gives you a very general interface to any debuggee in a terminal user interface. So knowing all of that, let's jump into the first set of examples here. So I've created this basic application. It's just a very simple executable that demonstrates how, for one, how you can use ghc-debug to look at the heap, and then two, how do we actually write an application that can be looked at with ghc-debug. So the first most important thing is that any debuggee that's being used by, or that is going to be analyzed by a ghc-debug debugger, needs this with ghc-debug function wrapping the main function, and that's it. And this function comes from ghc-debug stub. So to turn any Haskell application into a ghc-debug debuggee, you wrap the main function with ghc-debug, and then it's just normal your program from then on out. And what this with ghc-debug is what actually creates the socket and then forks and listens to the requests on another thread. So, okay, so that's going to create the socket. And then beyond that, I have just a normal application that reads an integer from the user. And then the first thing that I do is I assign this expression to the variable x's, and this expression is mapping the function +1 over the list from 0 to the number that was input. And I just assign that expression to x's, and then I do this save and pause thing where I'm wrapping the result, I'm wrapping this expression in a box. And the save and pause is a function that I wrote. Save and pause just takes a string that's just a description that gets printed out, and then a list of boxes where box comes from ghc-debug stub, and then it's IO. So what this does is it takes those boxes that it's given and then calls save closures from ghc-debug stub, which marks whatever's inside these boxes as being sort of saved by ghc-debug, so that in the ghc-debug brick user interface, we just have these closures available to us, and we don't actually have to do any searching to find them. So this will just make them available when I open up ghc-debug brick, the brick interface. And then I just pause, and it's an artificial pause. It's just a get line. So the program will just sit there until I press enter. So I call save and pause, where the only box that I pass is x's, which is this expression. And so if I run this heap shapes, you can see we get a message that says it starts ghc-debug on this socket, and the sockets by default just go into your attempt directory. And so if I enter the number 12, it pauses, and now we should, and obviously the program's artificially paused, so we should be able to open up this, we should be able to open up the ghc-debug brick user interface and connect to this debuggy and see what this looks like on the heap. What is this expression? What has it done on the heap? So ghc-debug brick. Open this up. So the first thing, and ghc-debug brick is just an executable. You can install it using cabal install ghc-debug brick. And what you'll see when you open it up is a list of the sockets that exist in that temp directory. And so these are all the sockets I've seen. If you're running it for the first time, you'll see just one socket under in the list here. And so here's the one that I want to select. It's my heap shapes application. So I select it. And then even though my program is artificially paused on my get line, we haven't actually paused the runtime system, the Haskell runtime system. So in order to do that, we have to send a request from our debugger to the debuggy to tell it to actually pause the runtime system so that we can do our analysis without the garbage collector moving things around. So I'll press P to pause. And now I see this window where the saved object that I called save closures on, which is that expression, the X's here, is at the top of the list. And then underneath that, we have the garbage collection routes of the runtime system. So we won't worry about these for now. We're just going to look at the saved object. And so we get a few pieces of information. Here is the memory address of the object that I saved, of this object on the heap. And then we know it's a thunk, and you can see up here the closure type is thunk10. And what this 10 means is that it's a thunk closure that has one pointer field and 0 non-pointer fields. So this thunk is pointing at some other object on the heap, and it has one pointer to some other object on the heap. The type of the thunk, or the result type of the computation that the thunk represents, is a list of integers, which makes sense because it's just mapping +1 over this list of integers. Now we get a little bit of other information. So I can move up and down in this interface, and then select this saved object, and then to expand it, I'll press the right arrow. And when I expand it, what the brick user interface does is shows what these pointer fields are actually pointing at. So this memory address here of the pointer that the thunk is pointing at is also the memory address here. So these are the fields that this object's pointing at. And this thunk is pointing directly at an integer, which this is the constructor for the integer type. And so it's pointing at the integer 12, which makes sense because that is the num here that I input as a user. And so this thunk is retaining all of the data that it needs to eventually run its computation, which makes sense because the computation is just everything else here except the num is kind of static. Like it can just run. So that thunk is pointing there, and that's all we can see. We can't do any evaluation in this window. All we can do is just examine these objects. And so this first example was a thunk, which is what we would expect because I didn't do anything to evaluate X's. I just applied the map function to these two arguments and then stored the expression in X's and then didn't do anything to evaluate it. So, and Haskell's lazy, so it's a thunk. The next example is taking X's, so the previous example, and then all I'm doing is forcing the expression to weak head normal form using the bang pattern. And this exclamation point here is what we call bang pattern, which means it's going to force this expression to weak head normal form. And I won't explain what weak head normal form is, but it's going to do a little bit of evaluation, and then we'll see what happens here. So weak head normal form is it's only going to evaluate down to the first constructor and nothing underneath. So it's only going to figure out, since this is a list, it's only going to figure out basically whether the list is empty or non-empty, and then it won't evaluate the head of the list, and it won't do any evaluation on the tail either. So what we expect to see here is that example 1 is no longer just a thunk, but it's going to be a list where the head is a thunk and the tail is also a thunk. So I'll resume by pressing Control R, and then I can go back to my application and say, hit enter to go to the next example. And then I can pause again. And now we see that the saved object is indeed a list. Yes, and what this says is, I mean, the way that ghc-debug brick displays this is that it uses the cons operator there, and so this is the head field of the cons constructor, and then the tail field of the cons constructor. And we can see the closure type is constr20, where this 2 means that it has 2 pointer fields, the 0 means it has 0 non-pointer fields. And so these are the 2 pointer fields that the cons constructor is pointing at. And if I open it up, I can see what those things are. And we see that the head is a thunk and the tail is also a thunk. And the head is a thunk that has another pointer field, so we can go even deeper. So, and the head of the list is a thunk, which is pointing at the integer 0. So this is a thunk that has 0 available to it, because it's going to need the 0 to eventually compute what this 0 plus 1 is for the head of the list. And then the tail of the list points to a function and 0 as well. And you can go really deep into the weeds about where this function is actually coming from. For now, I'll just say that the tail of this list, the function here, is going to be needed to compute the tail of this list, because it's coming from the enum from to function, which is what this dot gets desugared to.
Finley?
Yep.
There's a question for you.
Uh-huh.
Let me just bring it up here. This person asks, does it mean that the previously saved object is now lost in the brick view?
Yeah, so every time I call save closures, it'll remove any closures that I've saved previously. And that's just what ghc-debug does when you call save closures. Good question.
Thank you.
So that was that example, and we saw that it was a good example of what weak head normal form does. It only evaluated down to figure out that it's a cons constructor, not a nil constructor. So the list is not empty. It didn't evaluate the head at all, and it didn't evaluate the tail at all. So that's what the bang pattern did for us. And then next, we have just the length of that list. And again, we should ask ourselves, what do we expect this to be? Well, this example 2 is just the length function applied to x's, and then I'm not doing anything to evaluate what the length actually is before I box it. So again, we should just expect this to be a thunk. There shouldn't be no evaluation will happen here between the assignment or boxing it up. So if I resume, go back, pause again, it's just another thunk, but now the thunk points at the list x's that it needs to actually compute the length of the list. And the x's is still exactly the same as it was. It still has the head is a thunk and the tail is also a thunk that point at the same exact things. So next, that was the length unforced, but if I do the length of the list and force it to weak head normal form, this is going to force the result of this expression to weak head normal form. And so since the type of the result of this expression is just int, forcing an int to weak head normal form is just going to be the int, because there's no an integer in weak head normal form is just the integer. So if I do that, we should see that example 3 is just the length of the list. It's not a thunk. It's a fully evaluated int. And then what we should also see is that the length function had to walk over the spine of the list x's and go until it saw the empty list. And so the tail of the list should no longer be a thunk like this. It should just be another list. but none of the elements of the list should be evaluated. Like the list should be filled only with thunks, but we should be able to walk the entire list on the heap because it's gone the length function itself has gone the entire length of the list until it found the end to figure out how long it is. So resume, continue, and pause. So here I've saved two objects. The first is example 3, and that's, like I said, the integer. This I hash constructor is the constructor for ints. And that's the length of the list, 13, because I put in the number 12, and it was 0 to 12. And next is the list. And so this is just as it looked before, but now if we open it up, the head is still a thunk, but the tail is another list. And then the next one, the element is a thunk, and the next one's a list. And we can go all the way until we find the end of the list ourselves. And there it is. So the length function needed to go over the entire list and to figure out how long it is, but it didn't need to evaluate any of the elements. It just needed to figure out, it needed to find this nil. And so it opened up these thunks but it didn't evaluate any of the elements. Okay. So next example is maps. We're done with lists. Here's a lazy map where I'm building the list building the map using from list, and the pairs that I'm giving, the list of pairs that I'm giving from list is just same list from 0 to num, but the keys are the number -1 and the values are the number +1. So the keys as they are here are thunks. They're computations that need to be ran, and the values are also computations. So the values will be thunks at first and the keys will be thunks at first, but as we'll see, even well, I'll jump into this example. So I'm calling from list on this list of pairs and then putting in example 4. But again, I'm not doing anything to force any evaluation here. I'm just applying from list to this list, putting in an example 4. And so again, Haskell's lazy, so I don't do anything to evaluate it. It's just going to be a thunk, and there will be nothing else to it. So if I resume, pause, it's just a thunk. And again, it only points at num because num is the only thing that this expression needs. That's the only heap allocated thing that this expression needs to eventually compute its result. And so that's the only thing that the thunk points at. And now if I force that same expression to weak head normal form using the bang pattern, we will see that it'll go down to, obviously, you have to think about what the constructor of a map is, and we'll be able to examine the internals of this map. But kind of an important point about maps is that even lazy maps are strict along the spine because they need to know what order the elements, because internally the maps from the containers library are represented as balanced binary search trees. And so in order to even lazy maps are spine strict, basically. So the keys here are going to be evaluated and the values are still going to be thunks because the map, in order to even build a little bit of the map, it needs to know what order the keys are going to be in. So it's going to build the map, all of the keys, but the values are still going to be thunks because it's a lazy map. Resume, continue, pause. Okay, so here's a lazy map forced to weak head normal form. And bin is the constructor of a map node. And so you can think of it as like the node of the binary tree that is that this map is represented by. And so bin has 4 pointer fields and then 1 non-pointer field, which is this 13, which is the size of the map. So internally, maps cache their sizes using non-pointer fields like that. And the 4 pointer fields that the map stores is one being the key, which in this case is 6. The next being the value, which is a thunk, like I said. And the 6 is fully evaluated because it needed to know how to order itself internally. So the 6 was evaluated. And the thunk is the value here, which, since it's a lazy map, even though I forced this map to weekend normal form, it didn't force any of the values. So the value is still a thunk that points at the integer that it's going to need to compute the value. And then the next two are the children of this map node. And so if I expand the right child, the key is 10, the value is a thunk. If I keep going, here the key is 11, the value is a thunk, and then the two children of this are the tips of the map, which is another constructor of the map internally. So that's a lazy map forced to weekend normal form. Crucially, even though I force it to weekend normal form, these values are still thunks. And that's because it's a lazy map. And weekend normal form won't go farther than it needs to. It's not a deep evaluation. So now, next example is taking a strict map and then calling and building the same map, but just it's a strict map, and building it on the same list. It's the same map, but I'm using the strict variation of a map. And again, just to hammer it home, I'm not doing anything to evaluate this function application. So even though this is a strict map, I haven't done anything to evaluate the from list application here. So again, this next example is just going to be a thunk. It's a thunk, and it points at the integer 12 again and some function. But now if I force the strict map to weekend normal form, in contrast to the lazy map, the values will now also be evaluated to weekend normal form. Whereas with the lazy map, we saw the values remained as thunks. So going to that example. Here is our strict map forced to weekend normal form. It's the same map, so we still have 6 as the first key, and then 8 is the value that's mapped to by that 6. And since it's a strict map, that's why we see the 8, because the 8 got evaluated to weekend normal form. Since weekend normal form for an integer is just the integer itself, we see the 8. And we'll see that at every node of the map. Okay. Next example. I have a strict map, but now the map, instead of the values being integers, the map will hold maybes. And so I'm building the map in the same way, except I'm applying my own integer to maybe function on the values here. So if we look at what integer to maybe does, if the integer is 42, it's nothing. If it's not 42, it's just of this string. And so what do we expect to see if I build a map like this and I force the map just like I did previously? So the values should be forced to weekend normal form as well. But like I said about weekend normal form, it only evaluates to the first constructor and nothing beyond will get evaluated. And so because these are maybes, we will evaluate to see whether it's a just or a nothing in the values, but then not this computation here inside of the just will never be evaluated. It'll still be a thunk. So let's look at that example. Okay, here's the map, and the integer 6 maps to just, and based on what we know this integer to maybe function does, this should be just of the string that says was not 42, was 8. But the just, like I said, is holding a thunk. So even though we forced the strict map to weekend normal form, because the values are maybes, they have a constructor kind of surrounding them, and the elements, the data that's being stored in the just won't get forced. So this is still a thunk. And it's this thunk is the computation that would build that string that the just holds. So, okay, that's important to note. But what if I make my own strict maybe? So the default maybe is lazy in this way. If I make my own strict maybe type, where it's maybe prime, and I have nothing prime, and then just prime, but I put a bang on the A to say that whenever this gets evaluated, the A should also be evaluated to weak head normal form. That's what's going to happen. We're gonna if I use the strict maybe type in my map, just like I'm going to, we should see that this is no longer a thunk, but it is the weak head normal form result of this computation, which in this case, as we'll see, let's see what it looks like. So I'll resume. Move on. So here's the map. We have my strict just here, and it no longer holds a thunk, it holds a list, since it holds a string, which is a list of characters. And the first element of that list is W, but then the tail is still a thunk because we only evaluated the value inside this just to weak head normal form, and weak head normal form for a list is whether or not it's empty, and so that's how that ends up happening. Okay, so that's all the examples that we're going to do for heap shapes, and that's just a little introduction to ghc-debug as a concept, ghc-debug brick, and some evaluation stuff as well. And now let's jump into a real world application that I wrote for us to examine using these tools. So I'll leave ghc-debug brick. I'll stop my heap shapes application, and now I'll introduce the this application that I wrote that we're going to look at. So I call it the Haskell is obviously better at everything index, which abbreviates to HIOB index. I'm not sure how many of you have heard of the TIOB index, but it's a programming language popularity index, basically. And they rank Haskell really low, and so obviously I disagree with that. And so I wrote my own programming language popularity index, which is the HIOB index, and it's the one true indication of Haskell's popularity. So what the HIOB index is a server that serves some data from a database, and that database holds data that I got from the 2022 Stack Overflow developer survey. So it's just it's a SQLite database that serves a subset of the data from that survey. And then it allows people to query information about the data that's stored in that database and submit their own survey responses to the database. So just a basic web application serving data from a database. And this application, we keep some global state because we want to track some of our own statistics. So, and it's a Scotty web application. I should mention that too. It's a Scotty web application. So it uses the Scotty Haskell library. And we keep some global state. It's not incredibly important how it does it, but the state that we track looks like this. I'm tracking, so my global state, I keep an mvar, which stores the connection to the database there. And then I track how many requests have come in on the different endpoints of my server. And I track how many times the various languages that people are engaging with in the HIOB index. I track how many times each language is engaged with, just sort of basic statistics that I'm tracking there. But since I wrote the HIOB index for the purposes of this workshop, obviously it has some memory issues. And so we're going to sort of pretend that the HIOB index is like a black box. I know how it works. It's not incredibly important that you know how it works internally. So let's think about where we start. If we want to debug let's say we were pretending, let's pretend that we were running the HIOB index in production for like a week and then it kept crashing. And it was out of memory errors. So let's start thinking about how we can debug the memory issues that the HIOB index is having. So the first thing that we should do is just get, one of the best places to start is with the -s flag that we can pass to the runtime system. So I can run the HIOB server just like this, and I'll show you how to run it first. So I run the HIOB server just like a normal application. I already have the with ghc-debug wrapper on the main function, so that's why we see the starting ghc-debug message. And then since it's a Scotty application, I see the setting phasers just done message. And then on top of that, the web server just sitting here isn't very interesting for us to look at. So I also wrote some traffic bots that submit fake responses to the survey and then request random data from the application. So we can run the traffic for this application by running the HIOB traffic. And so we see all the requests going in and the submissions to the survey and all that. But we would like to start figuring out what's going on with the memory of the HIOB server, because something's wrong with it. So best place to start is to pass this runtime system -s flag, which tells the runtime system to emit some statistics, some garbage collection and memory and just program execution statistics once our program is finished executing. And the way that we pass runtime system flags to Haskell applications is by doing this +RTS and then followed by the runtime system flags that we want to pass. And in order to do this, in order to pass these flags, I just want to make sure that it's clear that I need some options. I think you might actually be able to pass the -s flag without this -RTS ops, but if you run into a problem using -s, then it might suggest to use this RTS ops. I can't remember exactly. Okay, but what it's going to do when I run it like this is emit some, when the program's done, the runtime system will print some statistics about our program's execution. So I can run the HIOB server like that. I'll run the traffic, and I won't run it for very long, and we'll see what it says is going on, what the statistics say. I stop it. Okay. And here's what the statistics look like from the -s flag. So it's a lot of information at first, but there's a few key things that I like to point at. First is this maximum residency stat, and this says how much data was allocated by was the runtime system tracking, was live or was resident on the heap at any given time. So over 48 samples, the highest that it ever got was 24 megabytes, which, based on what we know about what the HIOB server is doing, seems pretty high, because the HIOB server is not really doing much memory intensive work. It's not like, there's no reason it should be using 24 megs. And so that's our first sort of red flag. And then also we see another thing that to look at is this productivity. So we have an 84% productivity, which it basically says how much actual work was our program doing as opposed to like garbage collection. And 84% is pretty low. So that's another thing that might indicate that our program is not performing like it maybe should. And also, if we run this for shorter or longer periods of time, if I just run the HIOB server, so I ran it for pretty short there, but I'll run it for a little bit longer this time. And if we see, what we're going to look for is whether this maximum residency increases or decreases. If it increases significantly, then that would indicate that the program has some non-constant memory complexity that it shouldn't have, based on what we know the High observer is doing. So I've ran it for a little bit now. Let's go ahead and stop it. Okay, not stopping. There we go. Okay, so I mean, not much higher, not insane, not an insane growth there, but we could do it a couple more times, and we would probably see that it increases. And also, I think you trust me that this program has memory issues. So so we can think about what the next step is. Well, we know we have a very high level view of what our program's memory profile looks like now, and what we know is that it's using way too much memory, probably, and it's not very productive. Like it's spending a lot of time cleaning things up. So let's think about what's next. The next step that we're going to do in this session here is we're going to use the event log support that GHC has. We're going to have our program, we're going to have the runtime system emit an event log. What an event log tracks is basically what we can track. It tracks a whole number of things, but what we're going to care about is what allocations are happening of what types of data at what time. And then when we have the event log, we can use eventlog2html to generate a nice HTML page that shows us a nice graph of our program, of our program's memory profile. So in order to emit an event log, this one we for sure need a flag. We need a GHC flag or an option, and this dash event log is going to be required in order for our program to be linked with event log support. So if you have dash event log on GHC options, and then you can pass a runtime system flag, -L, to tell the runtime system to actually emit an event log. And then we have to tell the runtime system how we want the events that are put into that event log broken down. And the flag that I would start with is this -HT flag, which tells the runtime system to break down the events that it puts into the event log by closure type. So closure type is that thing that I was pointing at in ghc-debug brick, like the constr20 and the thunk10. So the data, the charts that we'll see in when we do eventlog2html will be broken down by those closure types. And that's what -HT does. And we can leave -S because we'll be looking at the high level statistics still. That won't hurt anything. So run the server with those flags, run the traffic. We don't have to let it run for very long. Just let the event log build up a bit. Okay, when I ran that, it created this hiobserver.eventlog because I told it to emit an event log. And if you forget, so very important not to forget this -HT, because if you forget the -HT, you'll just end up with an empty event log, and you'll be confused about why no data is in the charts. So you definitely need to tell it how to break down the events that it puts in the event log. And since I did that, we don't have an empty event log. The event log can be pretty big. This one is 176 megabytes. Earlier today, I had a 14 gigabyte one because I left it running for too long. And at that point, it's a little too big. Okay, so eventlog2html is what can take the event log and generate a nice HTML page that shows us the charts. And eventlog2html is also just an executable that you can install using cabal install eventlog2html. And so I'll run that on my event log, and I'll get a .eventlog.html file in my file browser. If I open that up, here is what gets generated by eventlog2html. Zoom in. So I hope that's visible. So the first thing that we see is this area chart, which breaks down, like I said, the allocation is on the y-axis, and then time is on the x-axis. And so we're seeing these crazy spikes of allocations happening, and the color of the color of the data here is what tells us what the closure type is. So here, the biggest spikes here are our words closures. Our words is like the byte, like the raw data, the underlying like byte string text, that sort of thing. Then we have list closures that are also a pretty big spike. We have text closures, also big spikes. Just big spikes. Stack it's spiky, but it's okay. Byte string, we start to see that there's some linear or like some increasing growth here, which is not good. Thunks are going way up. Thunks, we have a thunk leak for sure. And that's the thunk closure. This is thunk 2.0. Function closures are also going up. We can click through all these. We can only select one of these at a time. And then when you want to deselect one, just click somewhere over here that's not on one of these dots or the text. So you can click like over here, and it deselects and goes back to the normal view. Then there's the normalized view, which shows you the normalized stats stream graph. And then area chart is useful. I don't use normalized or stream graph very much, but line chart is probably the most revealing, because it's sort of like all of these lines are normalized to themselves, so it becomes very obvious which ones are having that like increasing behavior and which ones are and the spikes. So we see this group of closures that are all sort of leaking, and the allocation is only going up. And again, it's the thunk and the thunk 2.0 and the functions and byte strings are going up and that sort of thing. So the line chart makes that really obvious when you look at it like that. The heap view here, we see gives you some stats about the heap that I won't talk about too much, but live bytes is what the maximum residency from the -s flag would report. So these are the bytes that are actually live on the heap during our program's execution. And it like just crossed 24 megs. And if I go back over here, I can see that, yeah, we were right at about 24 megs during this run. And so we expect to see live bytes go right there. And then block size is bigger than live bytes, because with the way that the runtime system allocates data is it first requests mega blocks from the operating system, and so the mega block size is what is reported by the heap size here. So this is like what your operating system would report your program is using, which is way higher than the live data that gets reported by like the -s flag. And so this is, the operating system would probably report that my program was using like 56 megabytes. And then all those mega blocks that the runtime system takes control of, it chunks those into blocks, which then the live data gets put into. And so the blocks have some empty space in them, and the mega blocks are also not being fully utilized, which is why these two are bigger than the live bytes and the block size. So the block size is in between the heap size and the live bytes. And then you can see that live bytes is smaller than block size and heap size is the biggest. But this is useful if you're dealing with some other types of memory issues than we're going to talk about today. The detailed pane is nice because it gives us these little tiny charts of what the allocations look like, and it makes it very obvious which ones are sort of monotonically increasing here. And then and it's sorted initially by like magnitude, or I guess which one is allocating most. So like we saw, our words is all these spikes from our words is up top, and then thunk is leaking, thunk 2.0 is leaking, functions leaking, and we can sort by slope. This right here is the standard deviation calculation is a little strange, so these big numbers show up sometimes. We can sort by slope, which is kind of interesting. and I've done that in the past just to find which closures are leaking, if any. And so when we sort by slope, we see that we have a bunch of other stuff other than just like the thunk that is leaking. And so here we see we have a Scotty type body, the body cached Scotty type is also growing in a concerning way. We have a bunch of requests building up from the request type building up. We have hash map constructors building up. It's a lot of stuff here is building up. So that's all very concerning, and this is indicative of a big memory problem in the Hive index. So that's what eventlog2html can give us, is this sort of page, which is very useful. But we know what these things on the heap are that are causing issues, but we don't really know where they are or why it's happening. So in order to figure that out, we'll use a new facility that GHC has in it, which is called info table profiling. And this is available, I believe, in GHC's 9.2 and later. And what info table profiling does is, instead of breaking down the events that the runtime system emits by closure type, we can break it down by info table. And the reason that that's nice is because we also have these flags available in GHC 9.2 and later, I think, where these two flags specifically, f info table map and f distinct constructor tables. And what that does is an info table. I'll talk about what an info table is. An info table basically stores some metadata about a type or about a closure. And by default, all of these closures point at all equivalent closures. So like all of the text closures here will point at the same info table. So they'll have the same set of metadata, and that doesn't really tell so the info table doesn't tell us anything very useful for memory profiling. But when we use info table map and distinct constructor tables, all of the allocated closures no longer point at the same info table. They point at their own info table, which allows us to store more than just the normal metadata in the info table. It allows us to also store like where did the allocation happen, like source location and the module and more information like that. And so if I instead run the Hive server by doing not HT but HI, so breaks down the events that get put in the event log by info table, and then I also have these flags that make it so that the info tables are distinct for every closure. Then the the data that we can see in the eventlog2html generated pages becomes very useful. So run this again. Don't have to run it too long. Okay. Eventlog2html on the new event log that gets generated, and open it up. Okay, and now since I've done an info table profile, which as eventlog2html says is implied by the HI, then this area chart is no longer, we're not going to see closure types anymore. We're going to see these memory addresses, which are the info tables, which correspond to the info tables that each of those closure types that we saw in this event log will now point to. And so still we can sort of infer that these big spikes, that's the R words, even though it's this memory address, and then all the way down, and we can still see that some of these are leaking. But now, and in the line chart, we can still see it very, very obvious. But now, importantly, in the detailed pane, we actually get some nice source locations that tell us where these allocations are happening. And we see some type information. We see we can see the closure type here. So We won't worry about these spiky ones for now. We want to worry mostly about fixing these nasty looking leaks. So the first one that shows up is this thunk20, and it's a closure type of, it's a thunk. So these are some thunks that are leaking. And then the type of these, of the thunks. So what's going, like the computation that these thunks are representing, they are type mapped from text to integer. And they're being allocated in handlers.utils, and specifically on line 21. So that's a great spot to go look probably right now. So if I go to handlers utils on line 21, I can see that here is where I'm doing some of my global state modification. Specifically, this track lane function takes a language that someone has just submitted a request related to, and then it updates. It's supposed to update the state and like increment the counter that says how many times that language has been engaged with. So if I go to putlang is what's actually calling this modify function that I wrote, but putlang is calling modify, and it takes the high-ob state, and all it does is increment that language in the language engagements, part of the state. And so we can look at what modify is doing. Modify is the way that we have this global state in our application. Since it's a Scotty application, we have to sort of have this a custom monad for our handlers, where it's a reader surrounding a tvar of the high-ob state. That's how we sort of emulate global state. And so what the modify function does is it gets that tvar with the state in it, and then we call modify tvar on that tvar with the function that we're modifying with. And the modify in this case is taking the high-ob state and then incrementing that value in the map. And so we're seeing that this is probably a thunk. Something is not being forced in the way that we want it to be here. And if your application ever has global state, like 99 times out of 100, you're going to want that global state to not be thunky. You don't want any thunks building up in the global state. And that's true for the high-ob server too. So this is a mistake that this state, this computation specifically, becomes a thunk. And so we need to make sure that doesn't happen. And there's a couple ways to make sure that doesn't happen. Well, there's one way to make sure that it stops happening, and then a couple ways to make sure it doesn't happen. And one way that I kind of want to talk about, that I should talk about, is no thunks. And before I get into that, I see Edska, so everything's good?
Yeah, no, there's two questions about eventlog2html.
Okay.
So, Jason asks, is there a means of using the event log data without requiring the application to stop?
Without requiring the application to stop? Not that I know of. I don't think. I'm trying to remember. I don't think the event log I don't think you can use the event log while the application is running. There is not a way to do that right now. I think you have to stop the application and let the event log get fully written before especially before eventlog2html can use it.
Yeah, it used to be that you had to be really careful with this. Like even if you didn't terminate your program cleanly, like it was crashed or whatever, the event log would be unusable. I believe this is no longer true for recent versions of ghc/eventlog2html. So I think that's actually also there's a second question which is related to this, which is precisely this: like, is it still usable if the application crashes? I think the answer is yes, provided the ghc or eventlog2html is recent enough. For sure, the answer is no with older versions.
Mm-hmm.
as for using sort of an event log for a running application, like the event log is written incrementally, so in principle it should be fine. In practice, tooling might choke if there's some missing some missing headers at the end, and maybe actually also the current question that's still on the screen now. If there's really a hard seg fault, so the RTS doesn't get a chance to shut down cleanly at all, then maybe you will be missing that final header as well, or final footer, I suppose. And so tooling might choke on that. If that is true, it's probably a minor thing. Like in principle, it's written incrementally. So I feel like if this is indeed a problem, then it should be possible in principle to fix it, and maybe it wouldn't even be too difficult. But I do believe that it's like in practice with the tooling as it is now, that it's not possible.
Right. Yeah.
Okay.
Okay. Thanks. Good questions. So, like I said, we want to make sure that we're not introducing any thunks into our application state, because there's no reason that any of this should ever be thunky. Like we don't want this data to be lazy. We want it to be strict. And so like there's a number of ways that we can make it strict right now. Obviously, I know some of you know it, but we should ask ourselves too, how can we avoid introducing thunks like that into data like this? And one of the best ways to do that is using no thunks, which is the library that EDSCO has written. And what no thunks can do is guarantee that a value that you give it has no thunks in it whatsoever. And what you need to do to use no thunks is derive no thunks in this sort of way. So that's exactly what I do on high state. I derive no thunks, and then as a kind of corner case of data that you care to look at under no thunks, I'm also storing this mbar with a connection in it in my global state. And so obviously I don't really care that, like I don't want to look all the way into the connection and make sure it doesn't have any thunks like that. Yeah, I'm fine with that being however it is. And so the way that I indicate that to no thunks is by saying by using deriving via with the only check we code normal form wrapper for the connection when I make an instance for the connection type here. And so that's a side thing. What's important is that now that I have this no thunks, I can actually use the no thunks functions to make sure that any high state values don't have any thunks in them. And one of the no thunks has a couple ways to do that. The way that I'm going to do it is I have this unsafe check thunks function, which takes something that implements the no thunks class, and then all it does is it takes that thing, makes sure it doesn't have any thunks, and then returns it. Or if it does have thunks, it does something else, which we'll cover. But it calls unsafe no thunks, which results in either nothing if the thing doesn't have any thunks, so that's usually what you want in this case. And if it does have a thunk, it gives me a just of some thunk info. And so then I can choose what I want to do. Like you can imagine having no thunks using no thunks in your test suite to make sure that certain values never build up thunks, or yeah, that's one of the main benefits of no thunks, is that you can build it into your test suite and then get actual counter examples that say, like, okay, after this sequences of actions, I got this thunk happened in this value. And that's what no thunks really excels at, is making sure that not only the thunks are removed, but that they stay away, because you can build it into your test suite. And so here, what I've chosen to do is when I see a thunk, I'm going to unsafe perform IO, and I'm going to say that thunk alert. I'm going to show the thunk info, the call stack, and then I'm going to pause, and I'm going to look at the thing under the microscope of ghc-debug, just because that's a pretty useful workflow, and it shows sort of how these tools are kind of complementary. Like ghc-debug gives us very low level information about what this thunk is going to be. And nothunks has done a great job finding it and reporting it. And then most of the time, the information that nothunks gives you would be enough for you to figure out how to make your data strict enough that a thunk doesn't build up. But in this case, we can go a little farther and look at it under the microscope of ghc-debug. So what I'll do is I'll take this unsafe check thunks and I'll put it on, instead of just saying G here, when I modify with this function G, my state, I'm going to also unsafe check thunks. And now, after G updates the state, this unsafe check thunks will get the updated state, evaluate it to weak head normal form, which is fine. And then it's going to make sure that the weak head normal form of the high-ob state doesn't have any thunks inside of it. And so let's see what happens when I do that. I can leave these flags on, doesn't really matter. Okay, and when I run the traffic, right away it's going to find a thunk. So it found a thunk, so we get thunk alert. And then the thunk info that nothunks gives us is, it says thunk context. It's a map inside high-ob state. So it found that one of these maps in the high-ob state is a thunk, which is not good. And so, I mean, if this were more interactive or we had more time, we could actually sort of theorize about how we could change these if we want, like whether we want to change these so that the thunks are gone, or what we can do. But in this case, like I said, many of you probably know that the correct way to fix this, and the reason that this is happening, is because even though I'm using strict maps for my state, as you can see here, even though I'm using strict maps, this is not going to, this field of my high-ob state is not going to get evaluated, even if I force the evaluation of high-ob state, because weak head normal form of the high-ob state is only going to find the high-ob state constructor and not go any further. And so what I need to do is add some bangs to these maps in my high-ob state. When I make that change, we should see that, well, actually, I wanted to look at that in ghc-debug. So let's do that. So it's still thunky. Run it. Okay, now we can see what this looks like in ghc-debug. If I do ghc-debug brick, I see my socket for that run of the high-ob server. Pause, and I've saved the thunky state so that it's the first thing that I see when I open this up. And when I open it up, indeed, I can see that I have the mbar holding the connection, and then the first map in the state is a thunk. And it's pointing to this environment, and this environment is holding on to a bunch of things. It's holding on to that request that we saw in the eventlog2html output. It's holding on to another thunk, which is, and then functions, and these functions are holding on to things. And so even though, because we have a thunk in our state, like all bets are off about in terms of what our state could actually be retaining and how much data could sort of be waiting, and how much data could be there, like that we need for that thunk to actually compute. And so and ghc-debug is really good at showing us that, like, yeah, that's what's happening, is we have a thunk in our state that's keeping way more data than it actually needs. So it's better that we just evaluate it. And that's what we can do with the bang patterns on our state. Okay, and now when I run, we expect that no thunks will not say that will say there's actually no thunks. And the way it'll say that is by being quiet. So run the high-ob server, run the traffic, run the traffic. Okay, and now the traffic runs, and no thunks doesn't find any more thunks in our application state. And so that's where, and because we have this no thunks annotation, we are sure, if we built this into a test especially, we are sure that there will be no more thunks in our hyob state, because if we sort of build a check like this unsafe no thunks into our pipeline, then we can be sure that we will no longer introduce any thunks into this. And so that's really nice. Okay, but no thunks no thunks fixes thunks. It doesn't do any profiling really. Well, I mean, it does a little bit like it tells us there's no thunks, but that's about it. So let's go back to the eventlog2html profile and see what it says now. So I still ran the program there with the -ht. So I got an event log broken down by closure type, and I can do eventlog2html. It's a bit bigger of an event log, so it takes a little bit. Open up the event log, and we're still very spiky, but no thunks has helped us get rid of the leaks. So we no longer have this nasty increasing bar underneath the spikes here. It's getting a little bit bigger there. You can see it a little bit here too. So now it's completely flat underneath these big spikes. But these spikes are not thunks. There are some thunks here, but the spikes themselves are huge. They are, for example, this one, almost 11 megabytes, which is massive. And but these aren't thunks. So no thunks in a way can't really warn us against these huge memory spikes. So let's try to figure out where those are coming from. Just looking at the detailed pane like this in a profile that's broken down by closure type, we don't see much. We just see that it's R words, lists, text, stack, and some maybes, but we don't see much else. So let's break down the profile by info table. -hi instead of ht. Run the traffic. Wait a little bit. Okay. Yeah, and we're still seeing in the stats here, we're still seeing huge maximum residency, and we're still seeing very low productivity. So our program still has some fixing to do, obviously. Eventlog2html and that event log. Open it up. And now we have the info table profile, so we can go straight to the detailed pane and see that these spikes, these first two, we don't have much info for, but this next one that looks very closely correlated to those is a list closure that is specifically being allocated in the SQLite simple, which is a library that I'm using for the database access, the SQLite simple library. And it's a list, and it's happening specifically in this module. And we don't really have to go look at what's going on in this module, because now it's clear that, okay, these spikes are happening because of the database, the data that, like the way that I'm getting data from the database. And specifically, the spikes would indicate that we're doing like some huge in-memory computation, and that's where all the allocations are happening. And then we're reducing it down to some small result, and all of those allocations are just being collected. And so we need to. So let's look at the database code. That's what this info table profile has told us to go and look at the database. And so let's look at so one of the queries, or one of the endpoints that the Hive server has, is you can build a histogram that says how many times, or you get a histogram. It's just a map from language to number of times it's been engaged with, and so you get you can. This is the database function that builds that histogram, and the way that it works is I'm using the query function from the SQLite simple library, and I'm doing this query where I'm saying select this column from survey data, where the column is the language type. And the problem is that this query does not stream results. This query takes all the results of the query and puts them into a list, and then that's what I get back right here, is this list of the results from this query. And then I do a fold where I reduce that list into some small map from text to integer. And so that's where that huge in-memory computation is happening, where like the spike is happening when I'm doing the query, and all of the data from the database is being pulled in, and then the spike is going away when I'm folding that all down into the result of this call. And so what I need to do is figure out how to stream results from the database. And luckily I've already done that, where instead of using the query function from SQLite simple, we can use the fold function, which, as their documentation says, actually streams the results of the query. And so I have the naive non-streaming implementations of my database functions, and then I have the stream variants that are just suffixed with stream. And so I can go into my handlers, change each of these calls to these database functions to stream. And now, since all of those computations, all these spiky computations that were happening in memory are going to stream, we should flatten those spikes. Those spikes should be flattened. And we can verify that by doing a profile by closure type. So let's do that on the traffic. I'll let it run for a little bit longer this time. Okay. All right. Right off the bat, we see that we've gotten 98.5% productivity as opposed to last time 80%. So that was, those spikes were big productivity hit. And we also see that we've taken our maximum residency down from 20 some megabytes to a megabyte. And that's much better. That sounds much more reasonable. So let's look at what the event log looks like. Okay. Open it up. And we see a nice flat, non-increasing profile here. Yeah, that looks much better. This stack, this wall of stack, is not something to really be concerned about. It's very normal, and the allocation happening is pretty small relative to, I mean, it's nothing to be concerned about. 700 kilobytes of stack is not huge, and all of the data underlying this is all pretty standard. It's very flat. Nothing's increasing anymore. And the line chart shows us there's no obviously no obvious lines that are sort of shooting up anymore. And click through these, and the first time that I was clicking through these, I saw this line where we have the map node. So this is a closure type data.map.internal.bin. One of the let me find it. This, data.map.internal.bin. So the constructor of a map node in the line chart, and it looks like it's kind of got an upward trend to it. So it raised some flags, I guess, just because not entirely obvious right off the bat that this is going to stop increasing. Like maybe there's some error in the way that I'm increasing my state, and the map is just going to keep growing and growing and growing. So you might care to run the application a little bit longer to see to sort of hopefully see this flatten out. That's what we'd hope to see. And so while I'm explaining what this next part of the workshop is going to be, I'll run the application for much longer and hopefully give that time to flatten out. But another way that you can sort of do very low level either sanity checks or analysis of your heap is by writing your own custom ghc-debug debuggers. And so like, and when you see how flexible the libraries are, a bunch of ideas come to mind for analysis that you could write, but we'll go over a simple one that I've written today. So like I said, the ghc-debug brick application is like a generic debugger that can connect to any debuggy and give you some pretty useful, the ability to explore the heap of a debuggy. But you can get much more specific with the debuggers and the analysis that you can write with ghc-debug. And that's really like the killer feature of ghc-debug is how you can write domain-specific heap analysis for your applications. And the way that we do that is using the functions from ghc-debug client, which is this library. And ghc-debug client, like I said, has useful functions for writing heap analysis tools, which use ghc-debug. So it has a bunch of sort of pre-built, pre-cooked analyses that you can do for various types of memory issues like fragmentation. But we'll kind of go over how we can write just some starting out debuggers using this library. And you'll see how low level the analysis and how much control it gives us over the analysis that we actually do. So here I have in my debugger folder here a custom debugger that I want to connect to the HIOB state and that I want to run some analysis with. And my custom debugger is just basically a command line application where I can tell it to take a snapshot. One of the things that you can do with ghc-debug is take a snapshot of the heap of your application, and then you have that snapshot in just a file that you can share with someone else so that they can run analysis, or you can run offline analysis. You don't have to have your application running anymore. So that's nice. You can just take snapshots and then run analysis on those snapshots. And that's one of the other things that this debugger I wrote can do. So if you say snapshot and then give it a snapshot name, it'll take a snapshot. If you say debug and give it a snapshot name, it'll run the analysis on that snapshot. And if I just say debug, it'll connect to my running debuggy, the HIOB server, and run the analysis on the actual on the running application. So sort of and this is a good demonstration of like all the ways that you can run analysis with ghc-debug. So let's look at what the analysis is doing. So first, there's this concept of a debuggy in or this type debuggy in ghc-debug, which is an abstract representation of the actual application that you're debugging. And actually, before I do that, I'm going to stop this I'm going to stop and look at the event log because it probably got pretty big there. Only 2 gigabytes. Okay. So debuggy in ghc-debug is it just represents the application that you're connecting to and running the analysis on. And so this with debuggy connect is kind of one of the ways that you can connect to a debuggy that has a socket open. And so with debug connect comes from ghc-debug client, and I can give it the path to the socket that the debug has opened, and then I get this debug that I can run the analysis on. And so one of the things that in the snapshot case, all that I do is call make snapshot on that debug and then give it the snapshot name, and make snapshot will take the snapshot of the heap, write it to a file. So that's what that does. When I do my own debugging on an existing snapshot, I use the snapshot run function from ghc-debug client, and I give it the snapshot name and the analysis that I want it to run, and that's what it does. And then when I do the actual debugging, I use the with debug connect function again, give it the socket, and tell it to run this analysis on the live on the live debug instead of just taking a snapshot and then being done. Okay, so really quick, let's look at what that event log looks like. It's a bit bigger. We can see if those map nodes flattened out at all. Okay, so it's still flat. That's good. I don't see any obvious rising behavior. Line chart is illegible looking at it this way, but if I click through again, I see the map nodes are here, and it kind of does flatten out. Like you can see the kind of average line here. It goes up here and it flattens out, and it's increasing a tiny bit. So the analysis that I wrote for my custom debugger actually looks at these map nodes. So let's see what's going on. If I run, I'll just show you how this Hiob server, we'll take a snapshot, and I'll just run through these different modes of operation here for demonstration. So run the server, run the snapshot, or run the traffic. And now if I run my debugger and take a snapshot, if I do cabal run Hiob debugger and say take a snapshot and call it Hiob.snapshot, I need to tell it what socket to use using the environment variable. So that's the socket that one opened. Export, use this socket, run it. Okay, so there's some output here. Like if the heap were way bigger, then taking the snapshot would take way longer, and you would get a little bit of you'd see a few of these caching progress messages come out. But since our heap is small, we only see one, and we see our snapshot was created. So I can now do offline analysis using the snapshot. And before I do that, let's look at what the analysis is actually doing. Okay, so first, if I were going to run this analysis on a live debug, an actual application, the first thing that I need to do is pause, or else none of the other requests are going to work. None of the other requests over the socket are going to succeed. Our debugger is just going to crash and say it wasn't paused. So I say with pause, which brackets the pause and unpause, on this debug, do this analysis. And so the first part of this analysis is a very simple, basic example of some analysis you could do, is it counts the number of integers and map nodes that are retained by the Hiob state of the Hiob server. So you can imagine that our Hiob state on the heap is just this object at a memory address, and then it's pointing to the maps that it's holding, and those maps are pointing to integers. And because I'm a little concerned about this behavior here, I might care to do some analysis relating to these map nodes and the integers that the map nodes are holding onto. Yes, let's go.
Just this is a quick question from someone. Does snapshotting automatically pause and then resume the process?
Yes. Yeah. Good question. Yeah, it has to, just because don't want anything moving while you're taking the snapshot. So yeah. Any other questions? at the
Not at
moment?
the moment.
All right, cool. So like I said, first part of the analysis just is going to count the number of integers and map nodes that are retained by the high-hope state. And we're going to see that this is a little bit unexpected. So what I do is I use the run function from ghc-debug client. And the run function is what actually runs a debugger, like the debugger actions on the debuggy. So I say run on this debuggy, the one that I get during my analysis, run on this debuggy, this debug m action, which is like, this monad is sort of like you can think of it as the DSL that describes the debugger's actions against the debuggy, and give me back the results of that analysis in IO. And so the first thing that I do is request the garbage collection routes from the debuggy. And this GC routes function comes from ghc-debug. And what it gives me is a list of closure pointers. And a list of closure pointers is essentially just a list of pointers that point to some memory address in the heap. And what GC routes is going to give me specifically is the memory address of all of the top level, like the roots of garbage collection. So Haskell is a garbage collected language, obviously, and the roots of the garbage collection are what the garbage collector will start at when it's tracing the heap and finding any all the reachable data still, and then any unreachable data is what will be collected. In basic terms. So these GC routes are what the garbage are, like the actual sort of top level pieces of data that our program has allocated. And so all analysis on the heap sort of starts from the GC routes. And even in ghc-debug brick, like when I was running ghc-debug brick, the first thing that it showed us was all of the GC routes of the application. And I guess we can look at that. Just I'll make sure that I have the IOP server running. Server traffic. Okay, and then like in ghc-debug brick, the first thing that I see when I pause the application is the GC routes. So what ghc-debug brick has done behind the scenes is made the exact request that you saw in my debugger, GC routes, and then just put them, compiles them into a format that we can explore in the terminal. And GC routes are typically these things called TSOs, which are thread state objects, which are a runtime system thing that we don't need to worry about. But so what I'm going to get when I say give me the GC routes is this. I'm going to get this list of memory addresses, pointers to these objects on the heap that are up top. So I get those GC routes, and then from those routes, from that list of pointers, so starting from all of those pointers, I use the find retainers of constructor function from ghc-debug, which takes the number of paths that I want to find to this constructor. So I'll start by saying what a retainer path is. So obviously the HIOB server has a HIOB state object somewhere on the heap. Somewhere on its heap, it's allocated a HIOB state object. Hopefully only one. There should be only one. That's another bit of analysis you could do. But one HIOB state, and I want to find the path from a GC route down to the HIOB state. So I want to find what path I would have to traverse from one of these GC routes to actually arrive at a HIOB state. And what the find retainers of constructor function is going to do is take this limit for the number of paths that I want to find. So since I know there's one HIOB state, I'm just going to say find me one path. And then it takes the list of pointers that I want to start my search from, and it's going to search all of those pointers and find an object in the heap whose constructor is literally HIOB state, and that's the constructor of my state. And what I'll get back from that is a list of pointers, where now these lists of pointers represent paths from a route to my HIOB state. and since I've requested just one path, I just pattern match on the single path here. And then knowing this sort of invariant that the last entry in this path is going to be my high-hope state. So so I say last of this retainer path is going to be my root, which is actually like my high-hope state. So I'll rename this to be high-hope state pointer, technically high-hope state pointer. Root was a little confusing. So this is the closure pointer on the heap that points to the high-hope state, and that was the goal. Like the goal was of this, and when we look at what this analysis is doing at large, it'll be clear why that's the goal. But the goal is to find the closure pointer to the high-hope state, and the way that I do that is by finding the retainer path that ends with the high-hope state, and then taking the last element of that retainer path to keep the high-hope state. Then finally, what I do is build a heap graph of all of the memory that's sort of underneath, or the memory that is reachable from the high-hope state. That's what this build heap graph function from ghc-debug does. So I build a heap graph, and then this maybe int tells it how big of a graph to build if I care to limit that, because the graph could obviously be huge for some cases. And then it takes the closure pointer that I want to start, that I want to be the root of the heap graph, and then the closure pointer that I'm starting from is obviously the high-hope state pointer. So this graph that comes back from there is going to be a graph where the root is the high-hope state closure, and then everything from there is going to just be the data that's retained by my high-hope state. So the map nodes, the integers, all of those things. And the first thing that we can do when we have a heap graph is we can use the functions that sort of operate on heap graphs from the ghc-debug client library. And one of those is find constructors. It takes the string, which is the constructor name, the heap graph that you're searching through, and then gives you back a list of heap graph entries, which that type looks pretty much exactly how you would expect it to look. Heap graph entry has the closure pointer of the entry in the graph, and then the closure, which has a bunch more information. So I find all of the integer constructors by saying find constructors. And like I said earlier, the is is the constructor of the integer type, of the integer values. And then I'm searching in the graph that I built from the high-hope state. So I find all the integers that are reachable from high-hope state. And I do the same thing with map nodes, where the constructor name is bin. And then what I do is I output how many integers I found and how many map nodes I found. And because of the way that the state is represented, we would kind of expect there to be a one-to-one correspondence between the number of map nodes and the number of integers. And so if I comment out the rest of this analysis and we only run that analysis on the high-hope server, I'll do the debug option, which will actually connect to the running high-hope server and run the analysis. And so this is the socket path. Export. Use that socket. And if I run my debugger and I just tell it to debug, it should connect to the high-hope server, run the analysis, tell us how many integers are reachable from the high-hope state and how many map nodes are reachable. So it does that. Okay, it found 172 integers and 168 map nodes, which, interesting that there's 4 more integers than map nodes. If we run it again, it'll be a little different. It should change a little bit. So 175 integers, 168 map nodes. So there's some extra integers in there. And before the workshop, I was actually trying to, oh yeah, like in this case, 126 integers, 168 map nodes. So before this webinar, I was trying to figure out exactly what this was coming from, but now it's an exercise for the reader. And when I was investigating sort of this difference, I thought, okay, there's some integers being, there's more integers or less integers than I would expect there to be. notice that the number of map nodes stays relatively constant. We found one less here, but otherwise it was 168. So I thought, okay, well, let's look at all of these integers and figure out what they're being retained by. If we look at all the integers that are like, if there's extra integers being retained by the high-hope state, then it would be kind of strange, because all the integers should be tied to a bin, being a map node. And so if there's extra integers, like the retainer path should not show any bins. It should be something else. So if I include, so the way that I did that was, I get the retainer paths of each of these integers by doing find retainers of constructor, starting from the high-hope state closure pointer, which is the root of the graph. That's where I get that from. Pattern matching on the heap graph, and these are the graph roots. And since I've built it with using this function, there's a single root to this graph. So that's the closure pointer pointing at my high-hope state. If I find retainers of constructor starting from my high-hope state closure pointer, not limiting the search at all, so I'm going to find as many paths as there are integers, and that'll give me the retainer paths of all these integers. And the retainer paths come back as lists of closure pointers, where the inner lists are the paths. So it's the retainer paths. And then I have to use this function. I have to transform that in a way so that I can use this display retainer stack function from the ghc-debug library. Display retainer stack takes a list of pairs where the left element of the pair is a string describing this retainer path, and then the actual path itself, where we have to say where the path now goes through these like sort of specific size closure C and source information types. And so the way that we can transform that is by doing add location to stack on these retainer paths, which will make each of these into that list of pairs of size closure source or size closure C and the source information. And then I just have to zip that with a description, and all I do is just I do 0. I just number them basically, and then I get my retainer paths. So then I can display the retainer stack, all those paths, all those retainers that I care to see. And so let's see what this does. There's going to be a lot of integers because there's hundreds or over 100. So we'll see a bunch of retainer paths get output. And initially they look reasonable. Like here's the 176th integer retainer of this integer, and it's the integer 9. And then it is immediately retained by a bin node. So the map, like we expect, and then a high-hope state. So yeah, that's what we expect to see. We see it again there. And the high-hope state is obviously retained further by a tvar. That tvar in my reader in the reader monad of the application that I'm running. And then above that tvar is a stack, and then all the thread state objects that are that go to the eventual root of the garbage collection root. So we see that like this looks like we would expect. All of these integers are held onto by map nodes. And yeah, I mean, and then eventually you see something that we don't necessarily expect, which is the exercise for the reader, which is some of these integers, if we're lucky, once I scroll far enough. Yeah, some of these integers their retainer paths do not go through the high-hope state. They go through a survey response, which is my custom type. So it seems like some of these integers are making their way into the retainers, or into this find retainers of constructor call from outside of the actual high-hope state. And so that's an interesting thing that's happening. But if we had more time, we could dig deep into that, but I think for now, I think I'll just summarize everything that we've talked about today and start wrapping it up so that we can maybe move on to a few questions. So we started with heap shapes, where we talked about the ghc-debug model of debugging, where we have a debuggee and a debugger. The debugger and the debuggee talk over the socket, and we saw what the ghc-debug brick interface can do for us. We can see some pretty interesting stuff. Actually, just as for demonstration purposes, I will. You can actually even find retainer paths for things in the ghc-debug brick interface, which is very nice. So if I pause the Hiop server, and then the full key bindings are, if I press the question mark, these are all of the things that we can do in the ghc-debug brick interface. So right now I'm just looking at the save/gc roots view, but I can also take a snapshot, which is nice, that I can actually debug later. I can find retainers of constructors. I can find closures. So there's a lot you can actually do in this brick interface. And so if I find retainers of Hiop state, for example, as we expect, we see one Hiop state. And the first thing that we're going to see in the retainer, so it's first thing that we'll see are the fields of the Hiop state. So these are like what the Hiop state is holding, these fields. And then above that is the actual retainer path for the Hiop state. So this is what we were seeing in the output previously, going down to the Hiop state. And then we see the maps from text to integers and all of that. So we could also find retainers of integers, but we can't find retainers of integers underneath the Hiop state. So we're going to get way more than we really want. And well, here's one that we found that is who is retained by the Hiop state. So yeah, you can use the brick interface to find retainers as well and do more. But we get the programmatic the nice programmatic access using the ghc-debug client directly. So yeah, we've talked about ghc-debug. We talked about what eventlog2html, what the information that eventlog2html can give us, and eventlog info table profiling, what that advancement has done for memory profiling. Talked about no thunks. You have no thunks on your application state, and how that can help you prevent any further thunks from appearing in your state. ghc-debug is obviously great for low-level exploration of the heap. If you have some very hard, or if you want some very precise, if you want to ask very precise questions about your heap, ghc-debug is great for that. And yeah, I think that's kind of where I'll leave it if we want to go on to questions.
Thanks very much, Finley. That was great. There's a few, basically only one question at the moment, which is the question that was asked very early on in your presentation, but I thought let's leave it to the end, which is, does it work with all the backends, or are there problems with some of them?
That's a good question.
I can take it if you like.
Yeah, go ahead.
So my understanding is that whether the LLVM or the ASM, like the native code generation, that makes no difference. They are completely compatible in terms of the runtime. I think the WASM backend will currently not work, but I actually asked this internally within Well-Typed when this question was asked, and the general consensus is that it probably would not be too difficult to make it work. So if there's a specific need for that, then get in touch. But probably at the moment it won't quite work. So yeah. Then just a general comment from someone, which is somebody says this feels very powerful, the combination of these tools, and I think you and I can both agree that this is certainly something that we agree with. At least, I have been a professional Haskell consultant for over 10 years, And quite a lot of that time is spent helping clients with memory problems. And tools like ghc-debug and thunks have certainly made that significantly easier. So yeah, I totally agree with this.
Mm-hmm.
Let's see. Jason asked if there are facilities for modifying already available values of primitive types. Like,
Interesting.
could you actually modify the heap?
None at the moment, but there's been some discussion about that because like one of the first questions that always, and I like your question's a bit more nuanced, but like one of the first questions that always comes up when, like for me specifically when I was learning it too, was like if you've seen GHC Heap Viz, they have a way that you can like click to evaluate some thunk and get the result. And so I was wondering if there was a way to do that in ghc-debug as well. But the problem is that evaluation can trigger a garbage collection, which can mess everything up if like it can bring everything kind of out of alignment. And so for that reason, that there is no facilities for like evaluating things. As far as modifying like already evaluated primitive values, there's nothing for that, but I guess I don't possess the knowledge to know if that would be problematic through ghc-debug, but that's a good question. It's interesting.
It's probably possible. I mean, it feels a bit evil, but it's but I could imagine that in certain circumstances it might be useful.
Yeah.
Yeah. Maybe one thing we should point out is that all the code that Finley has been showing here will be available or already is available. I'll post a link in the chat in a second to a GitHub repo where you can find these examples, some documentation, a reminder of which flags to use. All those kinds of things are there. And also, I believe this video will be available on YouTube. So if you can watch it again if you need to. Or want to. I think there's a delay. There's like after the live stream terminates, there's some processing that happens, and then we can maybe cut the end and the start of the recording, and then it will become live. So, but it should become online. So there's one final question, at least currently final. Could you spare a few words about the exercise to the reader? And I'm smiling at this question because it's not a yes.
A few words. Well, I mean, the root of the issue, pun intended, is how some of these integers are not going through high state, right? Like, I guess, where is it? Most of them are, which is what you expect, but then some of them are going through this survey response type. If I find it, it was here. Maybe I just need to run it again. Yeah, I'll run it again. It's still running. Okay, so I think we're getting too many integers and we need survey. Okay, yeah, so here's an example. The retainer path, for the first integer that showed up this time. This integer is retained by a thunk, which is retained, and it's retained by a thunk, and the info table says that this allocation happened, or this thunk was allocated here. And then, I mean, that's a random spot. And then that thunk is retained by this just, which is coming from ASON, so some from JSON. And then that just is retained by survey response. And so if I look, I mean, that survey response type is coming from my little common library here. And so here, survey response, which has the languages that someone has worked with, the languages that someone wants to work with, and their yearly compensation. And so this this maybe integer is what is showing up in the path, is showing up in the integers kind of underneath the hyob state from this call in my debugger. So here, when I find retainers of the integers starting from the hyob state closure pointer, somehow this integer is making its way in there, and not entirely clear how, but that server response is retained by a function, one like my handler, it looks like, and then that function is retained by the stack. So somehow that's the source of some of those extra integers. And again, if we sort of run this without showing the retainer paths to see what the numbers look like. Yeah. 173. So I wonder if I stop the traffic, what's going to happen? Ah, there we go. Interesting. Very interesting.
So the real question is, right, why are we seeing these? Like, normally we would expect a one-to-one mapping between nodes in the map and integers being retained by the map, right? And we're not seeing that. Now, one, of course, it's possible that the map might not be in wicked normal form, right? Maybe it's reorienting itself, maybe it's rebalancing itself, right? So maybe one node of the map is holding on to some other nodes of the map because it's busy reorienting, right? Or maybe some part of the map is retaining some survey responses in order to compute some values in the map. All those things are possible, except not if the map is in wicked normal form. So if you want to get to the bottom of this, you need to say, well, if the map is in wicked normal form, why am I finding integers? Why am I not seeing this mapping? Like, the fact that there's other stuff being retained, there's other stuff in the application retaining integers is not the question, right? That's totally reasonable. The question is, why are we seeing them from the map?
Right.
And so that will be something to investigate.
Yeah.
All right. So I guess there are no further questions. So let me just thank Finley once more, and thank you for volunteering to be the first one to kick off this series. One more time, if you have any feedback on this format or suggestions for topics or anything like this, do get in touch. If you need help, we are available for consulting. Well-Typed is available, and we are hiring. So if you want to work for us or know anyone who might, also do get in touch. Thank you all very much.
Yeah.
And I will shut down the broadcast at this point.
All right.
Thanks all.
Thanks.